A wooden catapult has been widely used in Six Sigma education to illustrate multiple factor process variation and optimization. We will use a catapult simulator in Excel. We will use a catapult simulator with 4 factors to practice. Process variation, linear regression, response surface analysis, process optimization. Download this Excel simulator catapult.xlsx from Google Drive. Enable editing and run in Excel in your PC. We have 4 factors that might affect distance d. F. Spring force. M. Payload weight. A. Release angle. L. Lever length. Exercise working plan. 1. What factors affect distance? 2. What values of these factors to achieve maximum distance? 3. Run a full factorial set of experiments with 4 central points. 4. Can you detect curvature? Is this linear model valid? 5. Run response surface experiments to find a better model. 6. What is the resulting formula to estimate distance as a function of factors? 7. What values give us the maximum distance? 8. Make 10 replicates to estimate the confidence interval of the distance. 9. Calculate the angle A to hit a target of 20 with maximum or minimum values of F, M, and L. Based on our previous experience or process knowledge, we define the 2 levels we will use for each of the factors. First, we want to know which of these factors affect the range D. We will start with a full factorial design with the 4 factors adding 4 central points. See Article Design of Experiments, DOE, with Excel. In sheet coding we obtain the uncoded values from the coded design matrix. We will now simulate running these experiments entering the uncoded matrix in our simulator in Sheet Catapult. In Sheet Factorial, using Excel data analysis/regression. Input Y range are the outputs D. Input X range are the input factors. The R-square value of 0.68 indicates that this linear mathematical model only explains 68% of the variation. On the other hand, the p-values of the 4 factors below 0.05 indicate that they all have a significant effect on the distance d. Plotting distance as a function of angle, we see that the central point is out of line with the extremes. The relationship between distance and angle is not linear. This invalidates our linear model. We will try a quadratic model with response surface design of experiments. See response surface design of experiments with Excel. We will run a 4 factor CCD design in order to use the previous experiments already performed. To the 16 full factorial experiments already performed, we now add 8 additional star points and 7 central points to complete the response surface experiments. We now compute the squares and interactions of factors for the analysis. We do the regression analysis using D as an output and all factors, interactions, and squares as inputs. We now have a good R-square value of 91%. Those factors and interactions with a p-value above 0.05 marked in red are not significant, so we will remove the. We maintain factors F and L in spite of their high values because of their significant interactions. We now remove non-significant squares and interactions, p greater than 0.05, and run the regression again. The p-values for F and L are above 0.05, but their interactions are below 0.05, so they must remain. The resulting distance estimate formula is. We will prepare the cells for solver to calculate the optimal factor values to achieve maximum distance. We prepare the yellow cells to contain the values of f, m, a, l that solver will calculate to maximize distance d, R26. Squares and interactions in column R are calculated with formulas from the yellow cells. The formula for distance in R26 is the sum product of columns m and r. We will ask solver to maximize distance in R26 by changing the values in the yellow cells R18 to R21. We ask solver to maximize distance in R26 by changing the values in the yellow cells R18 to R21, subject to their constraints. Maximum distance is achieved with F equals 20, maximum force. M equals 1, minimum payload. A equals 60.6 degrees release angle. L equals 10, maximum lever length. We run 10 experiments, all with these optimal values. From the results we obtain the confidence interval of this maximum distance, from 68 to 75. The histogram of these values pass the normality test. With our fixed f, m, and l values, the relationship between angle and distance is. We now want to calculate the factor values to hit a specific target. There are many combinations of f, m, and l values that will allow us to achieve the target of 20 by changing the angle A. We fix f equals 10, m equals 2 and l equals 10 and use solver to calculate the angle A to hit the target D equals 20. The resulting angle is A equals 51.2. These are some conclusions. Process simulation could be a useful alternative when it is not possible to use an actual catapult to run these exercises. We can use an Excel simulator. Group work and discussion is still possible remotely, running the simulator as a shared file in the cloud such as OneDrive, while discussing via Zoom, Meet, or Teams. Design of factorial experiments and response surface analysis may be done with Excel data analysis. Excel solver may be used to optimize the mathematical model subject to constraints. You can read the article in Polyhedrica blogspot.